two key important steps on hydrogen energy, that is basically generation and then storage. So today I would like to share the views of utilization aspects of hydrogen, that is through PM fuel cells actually. So currently I'm sharing my slide, just to please confirm whether it has been shown there.
Sir, it is okay. So let me just check the presenter status there.
Yeah.
Sir, it is getting shared, sir.
Is it
Okay.
is it visible? Huh?
Yes, sir, it is visible.
Yeah. Okay. Okay.
Yes, sir, you can go ahead.
Yeah. So the topic for the discussion is today is that kind of PM fuel cell. We can call it as a kind of electrochemical engines. Actually, normally we do thermochemical engines and IC engines. Actually, we can also name it as a kind of electrochemical engines using that PM fuel cell, especially for the transport applications. Actually, it can also be used for stationary applications, but mostly for the transport applications, it's also being covered under this topic. In this hydrogen energy consortium, what we are discussed in day two is kind of production and then storage. So coming to utilization aspect, actually, as long as you store hydrogen and whenever you require the power, you can get it from fuel cell. So that is the last step of the hydrogen energy, apart from the production and storage. That is the ultimate step to use the hydrogen as the power generation fuel actually. So coming to the that is basic definition of fuel cell. I think most of them you are aware of that. As I said, the chemical reactions of 2H2 plus O2. So the combination of hydrogen and oxygen, not directly, in a controlled manner on the electrode surface actually. So you can get the pure water with the generation of power. So it produces electricity through chemical reaction, without not through combustion actually. So it operates like a battery, because battery is also producing a DC power and fuel cell also producing a DC power. But the main difference is that as long as you feed the fuel cell will generate power. Whereas in the cases of battery, it's a fixed electric charge stored in the form of materials actually. So once the material got exhaust or it is converted into a different form, then obviously the power output will be changed actually. So where in this case of fuel cell, as long as you supply fuel, it can generate power through the chemical reactions actually. So that is the major difference between the battery and then fuel cell. So what is hydrogen fuel cell? Because you can use any fuel, but why do you want to go with the hydrogen? Basically, it's basically a electrochemical cell, and it's generate power by reduction of air and by oxidation of hydrogen within the cell. And there are three important components, like it's a basically electrochemical cell. We need to have positive or negative, that is anode and cathode, then electrolyte actually. These are the three major component of fuel cell actually. So it's a it's a thermodynamically open system, and HFC uses hydrogen as a fuel and oxygen or air as the oxidant actually in a proton exchange membrane that will act as the electrolyte. I mean, in day two we discussed about the significance of the membrane. The same membrane, it can also be used in fuel cell, which will act as a electrolyte as well as the separator actually, because we are handling two different gases in the same compartment. So it should be a zero gas permeable and high ionic conductivity. So that is what the hydrogen fuel cell. And the main advantage is it is scalable, because you can make a fuel cell ranging from few watts to megawatt level actually. And the efficiency wise, it is quite high, 40 to 60%, because when you want to convert hydrogen into power, basically it can be converted to electrical power, DC power, and apart from the electrical power, you can also get the thermal energy actually. So altogether, the efficiency is slightly higher than the any of the energy conversion device like IC engine or whatever it is, and it is also reliable actually. So in sense of durability also, it's a well proven. For the stationary application, it's up to 40,000 hours of operations, and in terms of transport application, up to 5,000 operations has been demonstrated, and it is quite reliable and durable. and the kind of response, because when you try to use it for any automobile application, the response to the electrical signals has to be high. So in the case of battery also is good, and in the case of fuel cell also, especially these hydrogen fuel cell also on par with the other energy generation devices actually. And as I said, it's basically electrochemical cell. So depending upon the type of electrolyte which we are employed for making fuel cell, it can be categorized into 5 different types based on the type of electrolyte which we use. And second option is that a type operational, actually, whether it is a low temperature operation or high temperature operation. So in that category also, it can be categorized into 5 different types actually. So the first one is the proton exchange membrane based fuel cell, which is operating at low temperature, which can be used for portable to transport application. In entire range, we can use it actually. In the case of solid oxide fuel cell, because it's a high temperature fuel cell, this ion conduction is being happening through the oxide ion. So if you want to if you want to carry out the conduction of oxide ion within the material has to be heated to high temperature. So then only the oxide ion conductions will be possible. So in this case of a solid oxide fuel cell, it is operated at a high temperature of 1000 degrees Celsius. So because of this high operating temperature, it cannot be used for mobility applications, because it can be used only for the stationary application. And this molten carbonate and phosphoric acid salts are coming under the acid environment, but it has medium temperature actually. It's operate less than 1000 degrees Celsius, ranging from 300 to 900 degrees Celsius, and it can be used only for the generator stationary application because of the operating temperature range. And another last one is the direct methanol fuel cell, which is nothing but you are intuitively generating hydrogen from the methanol. So in hydrogen fuel cell, you have to pass pure hydrogen gas, whereas in the case of direct methanol fuel cell, you need to use direct methanol as a fuel. It can generate hydrogen within the system, and it can also power the system. So this is a direct methanol fuel cells. And among these 5 fuel cell, why do you want to go with the fuel PEM, proton exchange membrane based fuel cell? Is that basically the advantage is it can be scalable, ranging from few watts to megawatt level. So that is the advantage, and it can be used both for stationary as well as transport application. And the temperature is low temperature operations. So because of this advantage, this polymer electrolyte or proton exchange membrane based fuel cell gaining importance both for stationary as well as transport application. So if you see this basic configuration of fuel cell is that you need to have a membrane at the center, and both sides of the membrane, the catalyst has been coated actually. One is a positive, another one is the negative. So in order to facilitate the gas at each compartment, you need to have a flow channels actually, which is being taken on the graphite plate, and this flow channel is being determined based on the stoichiometric ratio required for the hydrogen oxygen in the system actually. So this is a typical single PM fuel cell configuration, and it is lightweight and compactable actually, because the membrane thickness will be in the range of micron, and you can make a very large stack because this repeating element of membrane and electrodes are very thin, and you can make a various modular of PM fuel cell. So coming to the important component which is involved in making proton exchange membrane fuel cell is that there are 4 important components. If you see on the right side of the slide actually, so the first is the membrane. It is called proton exchange membrane, which is nothing but it's a Teflon, which is Teflon backbone based polymer, which is being functional with the sulfonic acid group actually. The sulfonic acid group is responsible for the proton conduction within the polymer matrix. So this is one of the important component actually in the fuel cell. This is act as a electrolyte cum separator actually. So this is one of the important. This will act as a separator as well as the electrolyte for the conduction. And next important component is that bipolar plates. Actually, it's a separator plate because this is a graphite based bipolar plate. Because this graphite has a very good electrical conductivity, and in plane and through plane conductivity is good, and it has a very good thermal conductivity also. Because of these two properties, it is widely used as a bipolar plate for making fuel cell stack actually. So, so if it is a bipolar, then on the surface of the bipolar plate, you need to have a channels to facilitate the gas molecules in the respective compartment. And third important compound is the electrocatalyst actually. Normally the carbon powder, which is carbon supported platinum catalyst, which is being widely used as a electrocatalyst as a in the fuel cell actually. So, and another important, the fourth important substrate compound is kind of carbon paper or carbon cloth actually, which is one of the electrode substrate over which this electrocatalyst has been coated to make a electrode for the fuel cell. So these are the four important components for the single PEM fuel cell, and their function is depends on various chemical reaction which is taking place within the fuel cell. At the anode side, the hydrogen is getting oxidized and generating a proton. That proton has to be migrated through this membrane and reaches the cathode surface of the platinum on the another surface, and you have a oxygen molecule at this chamber, and you have a proton, and it is combined to form a water molecule at the cathode. So it need to have a hydrophilic properties and hydrophobic properties, and it should be porous in nature to facilitate the gas molecules. So these are the important properties and function of each component which is involved in making PEM fuel cell. And if you see these materials, as these are the four material. If you see the thickness of each material, because this electrolyte, it's ranging from 20 to 180 micron. It's a very thin polymer film, and over this polymer film, the catalyst has been directly coated. This platinum carbon is being directly coated on the membrane on both sides, and and you have a carbon substrate, that is carbon cloth or carbon paper, which act as a gas diffusion medium. It is porous, completely porous. It will facilitate to reach a gas molecule on the cathode and the electrode surface. So in order to facilitate the gas molecules, you need to have a separator plate, that is graphite plate, that is gas distribution plate or gas distribution cathode, that is called bipolar plate, which is ranging from 200 to 700 micron thickness. Mostly is made up of graphite actually, and it is has a desired flow channel to facilitate the gas molecule in the respective compartment. So these are the four important layer of PEM fuel cell. And if you want to have a multiple cells, this unit is being repeated simultaneously actually to get the required power from the fuel cell. And if you see this in terms of lifetime of the fuel cell, because when you want to make a fuel cell and you want to ascertain the life of the fuel cell, so the various phenomena which is happening within the fuel cell is most important. So so these various phenomena which is happening in the time scale of microseconds to month actually. So each phenomena will decide the life of the fuel cell actually. If you take some kind of double layer charging, because the electrode electrolyte interface actually, that is most important for any charge transfer or ionic mobility has to be taking place. Electrical double layer charging is most important. So that electrical double layer formation is happening in microseconds, but in the millisecond scale, if you see this, the gas diffusion has to taking place actually, because the gas diffusion has to taking place through the porous substrate to the catalyst surface. So that's happening in millisecond range. And then in terms of seconds range, so once if you the gas molecules, if it reaches on the catalyst surface, obviously the electrochemical reaction start and producing the water as a byproduct. So the water transport, so the produced water has to come out from the fuel cell. So that kind of liquid water transport, the membrane humidification, and the temperature will also rise slowly in the fuel cell. So these phenomena will happening in the range of seconds to hours actually. So all these phenomena will determine the life of the fuel cell over a period of time in terms of months or days actually. So all these phenomena will decide the entire life of the fuel cells. So the life is being ascertained based on the various phenomena happening in the time scale of microseconds to hours actually. So if you see the function of each component, as I said, the gas diffusion layer, which is nothing but a carbon cloth, has been coated with again carbon powder. So that will allow the gas molecule for the easy permeation to the catalyst surface. And as I said, the fuel cell, say for example, if you develop 1 kilowatt fuel cell, and if you try to operate for 1 hour, it also produces 700 ml of water over a period of time. I mean, in 1 hour. So this water is a byproduct of fuel cell. So you have to evacuate the water in a proper way. Otherwise, the flooding of water will happen within the cell. So you have to take care of the life of the PM fuel cell in proper way of uh, taking out the water from the fuel cell. So it must be have a, but at the same time, the membrane which is used in the fuel cell should be highly hydrated conditions. So the membrane conductivity, especially this proton conduction, will be higher only if the membrane is fully hydrated actually. So you need to have a balanced way of water management is crucially important. So the material which is being used in the fuel cell fabrication has to be hydrophilic as well as hydrophobic properties. So you have to process the material, especially the carbon substrate, to some extent, which will also allow you to stay some of the water within the cell, which is also allowed to evacuate the water from the cell. So the balanced hydrophilic and hydrophobic properties are essential in the within the cell to maintain the cell always hydrated in hydrated conditions actually. And another important component is the membrane. There is a proton exchange membrane. It's basically a Teflon polymer polytetrafluoroethylene PTFE. That is Teflon based polymer backbone, which is being functionalized with sulfonic acid groups. So that will allow you to take proton ion conduction within the two positive and negative electrode. And the main property of this membrane is should be highly mechanically stable. Though the thickness are in the micron range, it should be highly mechanically stable. Otherwise, if any pinhole formation happen within the membrane, so it allow the hydrogen and oxygen molecule for the direct combination actually. So it should be highly mechanically stability, and the thermal, in terms of thermal stability also, it should be stable up to 100 degrees Celsius in terms of physical, and thermal and mechanical stability is essential. And in terms of conductivity, it should have a zero electronic conductivity. It should not allow the electron to pass through the membrane. So it should be zero electronic conductivity, but at the same time, it should be highly ionic conductivity because the proton conduction has to be taking place through the membrane. So it should be highly ionic conductivity. And then low gas permeability because you are handling two different gases in the two compartment, and it should be completely free from the gas permeation molecule. So it should not allow any gas which is passed on the either side of the membrane. And in terms of stability and long-term stability also, it should be highly stable because the proton conduction should be always stable. Then only you can get the stable performance over a period of time. And the final component of the fuel cell is the bipolar plate, that is gas separator plate, because we have both side of the plate, you will have a desired flow channel. If you see in the figure, you have a desired flow channel. So entire both side of the plate has been grooved with a particular design to facilitate the hydrogen distribution on one side and air distribution on the another side actually. So that is why it's called as a bipolar. Each plate will have a positive and negative end on both sides. So the positive side, it will handle hydrogen, and negative side, it will handle air. And it has an inlet and outlet actually. So if you want to use this plate as a bipolar plate, it should have a high electrical conductivity, then on in plane as well as through plane conductivity. So the main requirement of the bipolar plate, it should be highly electrically conductive, and it should low gas permeability as like membrane. It should not allow the gases through the plate actually. It's a low gas permeability. And in terms of chemical and electrochemical stability, because you are operating the fuel cell at various potential range, so it should be stable at that particular electrochemical potential window, and particular pH, because it's acidic pH, because you are handling the proton within the membrane. So obviously the pH of the electrode near the surface will be acidic. So it should be highly stable in the acidic environment. And in terms of weight, it should be less than 5 gram per centimeter. The density of the plate has to be less, then only, because it's a repeating element actually. So if you have a high thickness plate, then obviously it will increase the overall weight of the fuel cell stack. So it should be highly mechanically stable, but at the same time density should be less. So these are the important features of the bipolar plate. The main function is that it will distribute both the fuel and oxygen to the electrocatalyst, and it will also facilitate the water management, because the water which is being produced within the system has to be taken out actually. So it should be uh, 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 it should be a water management actually should also be there. And as I said, the heat management, because 1 kilowatt fuel cell will also produce 1 kilowatt heat actually, but that heat is low grade heat. It's about 50 to 70 degrees Celsius, and you cannot use this heat apart from the room heating purpose. But at the same time, you have to maintain the fuel cell stack always at a particular temperature of 50 to 70 degrees Celsius. So whatever the heat which are being produced has to be evacuated. So the water or air is being used as the coolant. So it should be in a position to handle the coolant also within the cell. And mostly the graphite is being widely used as the bipolar plate. There are metals can also be used as a bipolar plate, but which is preferred for which application we can discuss in a subsequent slides actually. So as I said, once the plate is ready, and if you have a very plain plate and you cannot be able to precipitate the gas molecule within the electrode surface, so you need to have a proper flow channel actually on the plate. And you need to handle two different stoichiometry of gases actually, the hydrogen and the oxygen, because hydrogen is one mole of hydrogen and half mole of oxygen you need to handle to produce a power. So you need to have a different stoichiometric ratio on the flow field plate. So according to the stoichiometric ratio which we need to supply the air and oxygen, air and fuel, you need to have a different flow channel. So these are the various designs which is normally employed for any kind of fuel cell stack, ranging from grid or pin type. Mostly this kind of design is being used for the air movement actually, the straight parallel, single serpentine, the multiple serpentines. So these all the flow channels are being designed with the intention have a low pressure drop, and because the flow distribution has to be uniform, and inlet and outlet. So the pressure distribution, pressure loss should be minimum. So with the equal distribution of the reactant to the entire surface. So that is the main purpose of designing the proper flow channel on the graphite plate to facilitate the gas molecules. So the various, the one of the limitation is that in the PM fuel cell stack, 25% of the cost is goes to making this kind of fuel cell bipolar plate, and mostly, and it's also occupy more volume and weight to the entire PMPFC stack actually. So to consider these two aspects, we need to have a choice of choosing very thin metallic or graphite bipolar plate, and which is having very low density, so that you will get a weight and volume advantage altogether. And when you use the graphite, so though it is a brittle in nature, so you cannot reduce the thickness of the graphite plate beyond 3 mm or 4 mm. Okay, if you want to have a 100 cell in series, you need to have a minimum 100 plate in a PMM fuel cell stack. So that occupy more volume, and if you want to have such kind of stack for the transport application like electric vehicle applications, it occupy more volume and weight. So considering that, people are trying to replace the graphite plate with a metallic plate. But while you are going with a metallic plate, obviously the density of the plate is higher than the graphite, and you will not get a weight advantage. But you will get a volume advantage by making very thin metallic bipolar plate. So whereas in the case of graphite, you will get a volume advantage because the density is very low too, and but you cannot get a volume advantage because you need to use minimum 4 mm plate or 5 mm plate to have a desired flow channel on the plate, as well as to make a desired a kilowatt range of fuel cell. So to avoid that, people are trying to use a metallic plate with a very thin thickness. So if you use very thin metallic bipolar plate as a fuel cell bipolar plate, you will have a both weight and volume advantage. But when you are trying to get a more both weight and volume advantage, obviously the metal will have undergo corrosions under this acidic environment. So you need to take care of the corrosion property of the metallic bipolar plate actually. So so there is a target values which are being defined by Department of Energy actually. So the corrosion at the anode side should be less than 1 microamps per centimeter square. The same in the case of cathode side also, it should be less than 1 microamps per centimeter square under the potential limit of 0.6 volt actually. So the interfacial contract resistance, because normally when you want to avoid these corrosions on the metal plate, mostly stainless steel and aluminum and titanium. Among these three, the stainless steel is widely used, but the stainless steel may undergo corrosion over a period of time under this acidic environment. To protect that corrosions, people are trying to use different coatings, metallic coatings over the SS plate to avoid this corrosion and make it durable. So when you want to try to such kind of coating over the SS, you have to ensure how much of a contact resistance, because when you are creating layer by layer coating, obviously the interfacial resistance will also increase. So you have to reduce the interfacial contact resistance between these two layers, and you have to ensure the proper corrosion protections also. So these are the two important aspects of using metallic bipolar plate for PM fuel cell application. And in the so conventionally the graphite, now people are trained to use metallic flow field plate with a desired properties of conductivity, thermal in terms of electrical also, and the corrosion property, as I said, it has to be minimum. So, but even if you use a very thin plate, the challenge lying is that how you can make a desired flow channel. Because when you employ a very thin plate of metal like 1 mm or less than 0.1 mm or 0.2 mm, so when you want to make a desired flow channel, you cannot do the conventional milling over the metallic plate. It creates a lot of bend on the, and ultimately you will not get the planarity on the plate actually to make a entire PM stack. So there is a various strategy we try to employ to make a desired approach channel on the metallic plate. It's ranging from stamping, it's a conventional stamping. You have a die which is having desired flow channel, and do the hydraulic stamping method, you can get a desired flow channel on the plate. Or hydroforming, which is also industrially proven technology to make a desired channel on the plate. And additive manufacturing, so the 3D printing of kind of technology can also be employed for making a desired flow channel. And the chemical etching, because you can do a proper masking on the plate and do the chemical and it will etch the only unmasked area with a desired flow channel. And the chemical etching is also one of the way of making the metallic bipolar plate. And conventional milling, which is the energy intensive process and time consuming process. Among these five processes, the people are trained realizing that the hydroform method will be economically and cheaper, and even and it is being proven. It's one of the methodology to make a desired metallic, very thin metallic bipolar plate with a desired flow channel for the fuel cell application. So as I said, one of the limitation of metallic is undergo corrosion. We need to have a proper coating to avoid the corrosion in the acidic environment. And this is the various target values of metallic vapor plate in terms of cost, weight, and corrosion properties. And I can share these slides, and you can go through the what are the target values of metallic vapor plate if you want to employ in a fuel cell. And especially the stainless steel, as I said, is widely used as a metallic bipolar in fuel cell with a proper protective coating. That protective coating is being adopted through various deposition like physical vapor deposition or arc ion plating and thermal nitration, salt gel. There is a various kind of coating methodology has been adopted to make a desired uh, coating over the SS to protect the base material from the corrosion. And the titanium, aluminum, or nickel-based alloys can also be used as a base material, but these materials not being considered widely because of the cost nature, and there are some technical challenges in terms of aluminum when you want to employ in fuel cell. So it's the stability of the corrosion is not that great like SS. So the SS-based metallic bipolar plates are widely used for the fuel cell applications actually. So coming to the various phenomena happening within the fuel cell, apart from the component level what we discussed. So the next aspect is the kind of phenomenal. What are the phenomena which is happening within the fuel cell? So the first step is the water management. As I said, the membrane and the conduction of proton will be effective only the membrane is fully hydrated condition. So the water is being always produced at the cathode compartment. But if you are not properly eliminating the water from the cell, it creates a flooding at the cathode side, and it will not allow the fresh hydrogen or air molecule to reach the catalyst surface. So you have to take it out the water as soon as it gets produced within the cell. So you need to have a proper water management within the cell. So in order to have a proper water management within the cell, you have to make hydrophilic and hydrophobic coating over the component level surface actually, so that you can maintain some water within the system, so that you can always make membrane always hydrated. But at the same time, the 90% of the water which is being produced from the cell has to be evacuated. So you need to have a proper water management to have a stable and reliable performance over period of time of fuel cell. So, and thermal management, as I said, so for example, you develop a 1 kilowatt fuel cell and it is delivering a power of 1 kilowatt electrical power, but at the same time, it is also producing a 1 kilowatt heat, because the open circuit voltage is 1. Moment if you draw the load, the voltage will come down. So, and if you try to operate at 0.5 or 0.6, so the efficiency is close to 50 to 60%. So the remaining 40% of the energy is converted into heat energy. So the heat is also being produced during the operation of fuel cell. So as I said, 50% of the energy is coming out as a heat, 50% of the energy is coming out of the electrical power. So the heat has to be managed actually in a proper way with a proper cooling mechanism. So normally you need to have a normally in the PM fuel cell stack, people will introduce in between the coolant plate with a desired flow channel actually. So say for example, in between 3 to 4 cells or in between 2 to 3 cells, they will introduce a coolant plate which is having desired flow channel, which will facilitate the water or air as the coolant, and it will carry the produced heat from the fuel cell. So, as I said, when you want to have an effective thermal management system in the SIG, maybe closed loop cooling mechanism is preferred. So, you need to have a proper radiator with a closed loop mechanism, and you can effectively maintain the PM fuel cell stack at a desired temperature of 50 to 70 degrees Celsius. So, water is being widely used as a coolant in a PMFC stack ranging from 5 kilowatt to multiple kilowatt, whereas in the range of less than 3 kilowatt, air is being used as a very good coolant. So when you are selecting such a kind of thermal management system, so you have to consider the pump and radiator efficiency altogether, because the balance of plant power consumption has to be 10% of the produced power. That is the thumb rule. So because if you want to run the 1 kilowatt stack, you have to pass air. So how will you pass air? You have to turn on the compressor or blower. So the air compressor or blower power consumption has to be very, very less, but at the same time, it should deliver the required flow rate also. So identifying a proper balance of plant like radiators, pump, and air supply system, whether it is a blower or compressor. So all together, we need to take care, because all the balance of plant or balance of system has to be uh, consumed very less power. So it should be highly energy efficient, but at the same time, it should be highly compact. So these are the main criteria we need to consider while you are selecting the proper thermal management and water management. So apart from these two, the other important phenomena is contribute to the performance in terms of durability. So there is a four important negative phenomena may happening within the fuel cell that deteriorate the overall PM fuel cell performance. So one is the flooding. As I said, the water is being continuously produced in the cell. You have to properly evacuate the water from the cell. Otherwise, it will reduce the operating current density at a constant voltage. Second is starvation, which is nothing but when you operate the fuel cell, the fuel is being consumed at the interface, and you have to properly regenerate the fuel at the interface. So if it is not happened, then the fuel starvation will result in a negative fluctuating the voltage. Because of that, cell reverse, the anode become cathode and cathode become anode actually. So we should not allow the fuel starvation at the interface. So that way we can avoid this cell reverse current. And finally, the loss of catalyst activity over period of time. So how can we lose the catalyst activity? Because we use a very nanomaterials and micron range materials. So over period of time, these nanomaterials can combine together and form a bulk material. And if it bulk material, if it forms, then obviously the electrochemical active surface area of the material will come down. So overall, catalyst activity will also be coming down. So that all these four phenomena will result lower in the performance over long run. So coming to the power converter aspect, because fuel cell will produce a DC power. So when you want to convert into AC, normally you need to introduce a power conditioner. So normally you can introduce converters and inverters. And when you want to call it as a PM fuel cell system, it not only meant for the fuel cell, it also represents air supply system, a fuel supply system, and power conditioner, and entire control and monitoring system. So all together is essential if you want to make a PM fuel cell system actually. So in terms of power management, the critical aspects of the fuel cell is that you have though it is a DC power producing device like battery, but it is entirely different from the battery. The power electronics are entirely different from battery, because the battery, the power electronics is required is to meet out the operation of high voltage and low current. Whereas in the case of fuel cell, you need to have a power controllers, and power electronics is, it should be in a position to handle high current and low voltage. So because each fuel cell will produce 1 volt as a open circuit voltage. So moment if you draw the current, you can draw in 1 centimeter squared area, you can draw maximum of 1 to 2 amps actually. So this 1 to 2 amps has to be handled at 0.5 to 0.6 volt at a very low voltage actually. So if you have 100 cells in series, the multiple of voltage is close to 50 to 60 volt actually. But the current, you can, if you have a 100 centimeter squared or 300 centimeter squared, you need to handle 50 volt at 300 amps or something like that. So you need to in a position to develop a power electronics which can handle high current at low voltage, not at low voltage, not at high voltage and low current. So the power electronics is also playing a major role in getting the stable power from the fuel cell actually. And apart from these power electronics, power management, thermal management, and water management, so the how do we control the parameters, and what are the strategies which we need to employ when you want to develop a control mechanism for the fuel cell? Because most of the control strategies is driven by the voltage driven, but in the case of fuels, it is a current driven logical system is required. Current driven process is required in the case of fuel cell when you want to employ a control and monitoring system, because so the current will determine the entire operation of the fuel cell. The current is nothing but the load actually. So the current, because when you have a more current, when you draw more current, the more heat, the voltage will come down. Because of that the heat generation will be more, and the water generation will also be more, the fuel consumption will also be more. So air consumption, obviously the oxygen consumption will also be more. So the diffusion, all these phenomena is being controlled through the current, not through the voltage. So the when you want to develop a control strategy for a fuel cell system, it should be current driven control strategy, not voltage driven control strategy. So with this fundamental background of fuel cell, so what we are currently doing in our research center is that, so this is our pathway mechanism for the development of technology. So we adopt two pathway mechanism. One is starting from commercial materials. So in the middle of the journey, we will take a commercial material, commercial electrocatalyst, commercial membrane, and commercial carbon substrate, and commercial plate. So, and we will start to make a component like a catalyst coated membrane and membrane electrode assembly and bipolar plates. We will make a component from the raw material, commercial raw materials, and we will make a short stack and full stack. So once the stack is ready, we will develop the all the balance of system, that is air supply, fuel supply system, thermal management, power management, all coolant management, all this balance of system we will develop, and we will try to integrate with the fuel cell stack and make a product actually that has been employed for various field trials. That is one of the pathway mechanism. And second parallel pathway mechanisms that we can also do our own material. We will develop our own material, not like a commercially raw materials, and we will evaluate in a common level with the materials. Once if it is success, then we will make a small single cell, and that has performance has been compared with the commercial material. If it is on par with the commercial membrane, then we will think about the scaling up of our R&D activities to the system level actually. So this is our two-way pathway mechanism for our technological development. And this is our journey of developing various fuel cell complete grid independent power supply system ranging from 1 kilowatt to 20 kilowatt capacity with all the required balance of system over a period of time. And whatever the system which we develop, we will normally employ this fuel cell system wherever the hydrogen is available actually. So we will put up our hydrogen system wherever the hydrogen, and we will monitor the actual performance of the fuel cell system which we develop. And this is our various field trial demonstration which we carried out, and especially the Baba Atomic Research Center and Gas Authority of India Limited, Naval Lignite Corporation, which is one of the power plant which is located in Tamil Nadu, and all that they have their own hydrogen, and using that hydrogen, and we will put up our system and we will generate power for their application actually. So this is a kind of demonstration we widely carried out actually in various PSU. And apart from that, we try to demonstrate as a kind of a hydrogen truck actually, where the truck is though is being powered the diesel truck, we will have all the inbuilt PM fuel cell system with the gas cylinders actually. So we have hydrogen gas cylinders and we have a fuel cell in the vehicle. And whenever some disaster management, so if any floodings happens, then if its immediate power requirement is if is required, then this truck can power the meet out the required power demand. As a kind of proof of concept with the Tamil Nadu government, we did a kind of a disaster management with our 5 kilowatt fuel cell system. It can power maximum of 5 to 7 kilowatt with the immediate to meet out the immediate power demand actually. And apart from the stationary application, nowadays the PM fuel cells is being considered one of the power backup application for telecom tower, because the telecom towers mostly depends on grid. When grid is failure, they need to have a failure to handle the failure mechanism with a diesel genset that is normally employed in various telecom tower. But the government regulatory is pushing them to go with the non-carbon route, that is fuel cell route actually. So we have approached some Airtel Telecom tower in Pune, and we try to demonstrate our fuel cell system as a kind of backup power application whenever the grid power is failure. So we will our telecoms telephone, I mean our PM fuel cell will power the telecom tower during the grid power in the absence of grid power actually. So that was a decent demonstration which we carried out, and many telecom tower operators are looking for alternative backup power applications. So the hydrogen fuel cell is also one of the power backup application, and many data centers are also looking for immediate application of fuel cell for the telecom tower as a stationary backup power application actually. And as I said, when you want to make a fuel cell stack, it requires starting from materials to, and material has to be processed and it has to be assembled, and it has to be delivered as a fuel cell stack. So the entire steps involves about 45 steps are involved when you want to make a fuel cell stack actually. So earlier we tried to automate about 30% of the process has been steps has been automated. Now we try to make a maximum of automation step, which we try to employ while fuel cell component as well as stack fabrication steps actually. and it's a kind of unique facilities and first of its kind in India. We developed and this is the various processing steps involved in making fuel cell stack, ranging from carbon material, how to handle the carbon cloth, and it has to be teflonized to make hydrophobic properties, and the gas efficient layer has to be coated, and the catalyst has to be directly sprayed on the membrane to make a catalyst coated membrane. And once this CCM is ready, that is catalyst coated membrane is ready, has to be sandwiched with a gas diffusion layer to make a membrane electrode assembly. And then once ME is ready, that ME has to be placed in between the two bipolar plate, that is called graphite based bipolar plate, that has to be gasketing. So all the steps as we try to automate with a complete automation process and robotic assembly. And this is our layout of established automation layer of making PM fuel cell with a component level at the stack level. And this is the photograph of the our established automation line for making fuel cell stack, ranging from materials to stack. So it's involved various stations actually, and it is one of the unique facilities, and we try to establish in our premises, and it can handle up to 100 kilowatt per year of hydrogen, I mean fuel cell stack can be produced from this pilot line actually. And coming to the stationary, apart from stationary application, in terms of transport application, so whatever the stack which we fabricated within our lab, we try to integrate with a battery, and it's a kind of range extender. So we did a demonstration for the two-wheeler as well as go-kart, and for the four-wheeler also, we did as a kind of demonstration for the four-wheeler as a with a battery as a range extender actually. So so we did a lot of trial in our premises, and it shows the feasibility of using integrating with the hybrid with the battery, can also be used as a hybrid vehicles actually with our own fuel cell. And apart from the converting hydrogen into power through fuel cell, there is a ICE engine can also be used for the hydrogen converted to power. But the challenge is lying is that the kind of air fuel ratio is more, because it's a hydrogen gas. Obviously, it occupies more volume in the combustion zone actually, and there may be a possibility for the NOx emission, which is higher than the I mean fossil fuel based engine. So we need to take care of the NOx emissions when you want to employ a hydrogen ICE engine, and and the efficiency base, it's not on par with the fuel cell. It's a low efficiency, is close to 25 to 30%, and not with the 40 to 50% what we are getting in fuel cell. And normally the fuel cell car works in such a way that anyway you will have a battery back because to get the stable power out of fuel cell, and you have a booster converter because fuel cell and inverters to power the traction motors, and that will take care of the final drive through the wheel actually. This is the typical mechanism of fuel cell cars works actually. And in this fuel cell hybrid vehicles, there is a two different hybrid actually, whether it's series and parallel. In the case of series hybrid vehicles, the fuel cell part will be small, the small fuel cell and large battery bank. So mostly the battery drives motor at all times, and fuel cell operates continuously and keeps battery always charging actually. So that kind of mechanism is also being adopted. And in this case, the fuel cell is not load following actually. The battery will be the load following, but fuel cell will support the battery actually. So that is called series hybrid. In the case of parallel hybrid, the fuel cell will control the motor actually, will follow the load actually, and not the battery. And the battery size is small and the fuel cell size is high. And the fuel cell drive motor at all times. It's load following, not battery. So battery provides a boost power whenever if any surge in current or surge in voltage through the fuel cell. So the battery will provide the booster power, and when as and when it is required to power the motor actually. So this is a various two different kind of hybrid vehicles, fuel cell hybrid vehicles normally people will employ for the commercial applications actually. So when you want to have a fuel cell hydrogen electric vehicle on road, the major requirement of the is that it should be cost competitive. The first one is, and the fuel cell system alone must because it should have a sustained speed of maximum of 160 kilometers per hour, and with the assist of electronic supporting system and fuel cell control system, it should allow 0 to 95 kilometers per hour speed in 10 seconds. That is a kind of response has to be there, and this transition response is 1 second transition response time from 10 to 90% of the power, and fuel cell system must reach maximum power of in 15 seconds in the case of cold startup, and 30 seconds in the case of cold startup, and 15 seconds in the case of ambient temperature actually. So these are the various key parameters required for fuel cell hydrogen electric vehicles, and these are the key component which is involved in the fuel cell electric vehicles. So as I said, the battery and the motor and the control thermal management system, the radiators and power electronic controllers and are most important. And the fuel filler also is most, it's a nozzle which is also one of the costly component in the dispensing station. So the nozzle from high pressure dispenser which is attached to the respectable on the vehicle of the filling tank actually. So the nozzle which need to be handled high pressure to low pressure dispensing, and the battery the store energy which is generated from the regenerative braking system and provide supplement power to the electrical traction motors when as and when required actually. So these are the key component which is involved in the fuel cell electric vehicles, and various automobile manufacturers are already developed and demonstrated, and commercially the fuel cell hydrogen electric vehicles are there, and the Honda and Toyota and the leading automobile manufacturers, so they have already deployed this hydrogen fuel cell vehicle. Especially I can also when I could able to experience this Toyota Mirai when I was in Canada. So it's a good vehicles, and it is has a 700 bar hydrogen um, pressure cylinders is on board, so that is meet out the entire range of the fuel cell electric vehicles. So most of these electric vehicles are operating at high fuel cell power and low battery power. It's the range of the fuel cell you can see on the top of the photo, the fuel cell which is being placed on the front of the fuel cell, I mean vehicle. So it is about 120 to 130 kilowatt fuel cell. It's so compact, which is made up of metallic bipolar plate, what we discussed. So it occupies less volume and less weight, and it can handle up to, it can deliver up to 120 to 130 kilowatt of power, which is required to for this vehicle actually. And when in terms of battery vehicles, when we try to compare battery electric vehicle and fuel cell electric vehicles, there are three important parameters which we need to consider. One is price and range and time to refuel. So these are the three important parameters normally people will compare battery and fuel cell electric vehicles. In the case of hydrogen fuel cell vehicle, in terms of time to refuel, it is on par with fossil fuel based vehicles. And in terms of charging, the electric vehicles require higher charging times ranging from half an hour to 12 hours depending on the battery type. And in terms of range also, it is on par with the fossil fuel. So we can cover 300 to 400 kilometers like a petrol and diesel engine. And in terms of price, right now it is costly because of the low volume, but over period of time, it can also meet out the electric vehicle charger, which is normally used for the fuel cell, I mean, lithium ion battery based electric vehicle actually. So, but though the demonstration and the and pilot studies has been carried out, and even commercial vehicles we could able to find out, but if you want to have a deeper penetration in market level, there are some key challenges still need to be addressed. The main one of the component is that the cost of the fuel cell. So right now it is slightly higher because of the low volume, so the people are trying to reduce the cost about $30 per kilowatt. So if it can able to meet out that cost demand, then the market penetration will be much faster. And in terms of durability, because the fuel cell life will be higher for the stationary application. The reason is that when you want to employ this fuel cell for stationary, there won't be any frequent start-stop cycle actually. So when you do the start-stop cycle very frequently, obviously the electrochemical phenomena will be different. So that hinders the life of the fuel cell. So it is in terms of stationary application, it is being operated at a constant load, That's why the durability of the fuel cell is close to 30,000 hours to 40,000 hours. Whereas in the case of transport applications, it's aiming only for 5,000 hours actually, because it's a frequent start-stop cycle. So when you do the very frequent start-stop, obviously the hydrogen-oxygen crossovers may happen that deteriorate the fuel cell performance over a period of time. So especially for the transport application, the life is reduced to 5,000 hours. So and as I said, the balance of plant, which is also developing a balance of plant, because very compact, high energy efficient blow air supply system and thermal management system, radiator system, and power converters. So these are all essential other BOP components apart from the stack. And this cost of the BOP components also slightly higher right now. So because we don't have a such kind of infrastructure in India to make such kind of very precise and high energy efficient BOP components required for the fuel cell. So once if it comes, then obviously the cost of the entire PMF system will also come down. And finally, the fuel infrastructure, which is also key important actually, because even if you have a fuel cell vehicle, if you don't have a charging station, then it is not possible to realize the hydrogen fuel cell vehicle on the road. So the creating a fuel infrastructure is also equally important. So there are a lot of momentum right now is being taken by our government to create a model or demonstrated of a hydrogen dispensing station, and recently it has been launched in Ladakh actually. So we have a hydrogen filling station. So slowly it is coming up. Once the fuel infrastructure is created, obviously the fuel cell vehicles we can see on the road. But obviously any new technology, there is a drive. I mean there is a competition between the cost and price actually. So any new technology, if you want to implement in the commercial application, obviously we need to be compromised on the margin so that the technology penetration to the market will be easier. So the price has to be reduced considering with a low margin actually. And with that actually I stop here, and I am open for further discussion.
Thank you very much, sir.
Yeah.
Very wonderful session. Sir, there are questions in the chat box.
Yeah, I will take one from my. So there is a question from Raju Kurjan. How does the fuel cell electric vehicle handle sudden acceleration demand since they don't store electrical energy as like we? Yeah, it's a very good question actually. You are correct actually, because fuel cell, as I said, though the open circuit voltage is say for example, we have a 100 cell in a stack, it generates 100 volt, and once moment if you draw the load, it comes to 60 volt actually. That is a zero point 0.6 volt per cell. So this 400 to 60, the voltage transition will happen in microseconds or milliseconds actually. So, but at the output, you need to have a constant voltage. So in that case, there is a super capacitor. Our battery is helping to meet out the stable power which is required for any traction actually. So that way, the fuel and the response to the fuel cell is also quite good. And there are converters, power converters is are available to handle the wide voltage window of 100 to 60, which is happening within milliseconds or microsecond. So the designing the proper power management actually, and there is a methodology control systems also being well established. Load following gas flow controller, because as soon as you the demand of the load is more, so depending on the feedback control basis, load following gas flow controllers are well established, which are being integrated as a part of the system. So load following gas flow controllers and stable batteries or another energy storage medium like supercapacitor will meet out of the stable power which is required for the any traction or any application, actually motor application.
Dear participants, if there are any other questions, So the session is open now for the Q&A.
Hello, sir.
Yeah, there's another question from Sandeep Kumar, I think. So what is the fuel cell stack efficiency? Yeah, basically in terms of efficiency, energy efficiency is close to 80%. The 40% goes to power and 40% goes to thermal. So hydrogen to energy, it's about 80%. The 40% will get electrical power and 40% will get thermal energy.
Sir, there is one more question we have sent privately
Yeah.
to me. Yeah, sir, the question is, does the supply of oxygen instead of air
Yeah.
into the fuel cell stack, does it improve efficiency the marginal
Yeah.
amount or not?
Exactly. Actually, normally for any commercial application, the oxygen is not being widely used actually, because if you want, especially for the transport application, you need to carry two different cylinders actually. So the oxygen is not being preferred for the mobility application. Even for stationary application, it's expensive. So normally air is being used as a oxygen. But if you say for example, you have 1 kilowatt system, when you try to operate the 1 kilowatt system with air, it is designed for air. So hydrogen and air, it can produce 1 kilowatt. But if you have a pure oxygen, you will get the double the capacity of the power actually. So the same 1 kilowatt will produce 2 kilowatt, because the stoichiometric in the air of oxygen, in the air it's about 17%. Actually, you need to 5 times flow rate of air has to be more, and the partial pressure of the oxygen in the air is also very less. So these are the parameters which will slow down the entire entire reduction reaction of the oxygen side. So if you have a 1 kilowatt system which is designed for hydrogen in the air, will give 1 kilowatt. But the same system, if you try to operate with hydrogen and oxygen, it can deliver 2 kilowatt power.
Sir, there is one more question from the last session. So
Yeah.
participants have messaged me.
Yeah.
What is the expected life of proton exchange membrane?
Yeah, you're talking about only the membrane or entire system actually?
The question is simply about membrane, sir. Proton
Yeah,
exchange membrane.
membrane has been proven. It's quite stable, but depending on the application end actually, because the same membrane is, if it is used for the fuel cell applications, especially transport and stationary application, it ranges from 5,000 hours for transport and 50,000 hours for stationary. Whereas the same case of membrane, if it is employed for the electrolysis application, so it has been proven up to 10,000 hours actually. So the membrane stability depends on the application end. So whether it is being used as a stationary application or it is being used as a transport application. So the membrane will be stable quite long time, but other component like catalyst and the bipolar plate and the frequent start-stop cycles, so all the operating parameters will decide the membrane lifetime actually. But as of now, it is proven it's more than 50,000 hours, it is stable actually.
There is one more question also, sir, on the membrane only.
Yeah.
It states like this. So apart from the rupture of membrane, what are other reasons for the failure?
Yeah, actually, it's a good question. Basically, apart from the rupture, over period of time, because the water is also being continuously produced, and you need to operate the system slightly elevated pressure of 1 to 2 bar pressure or 3 bar pressure in the case of metallic bipolar phase stack. So in that conditions, over period of time, the membrane thinning will happen actually. So say for initial thickness of the membrane is about 20 to 25 micron or 50 micron. Over period of time, the membrane thinning, because when you do the main reason for reduced lifetime in the case of mobility application is that you do frequent start stop of actually engine start stop is frequent. So during that time, the membrane in on time the membrane will be highly humidified. In the off time, it is completely dehydrated. So it undergoes hydration and dehydration condition very often when you employ the membrane in a transport application. So such a kind, if it undergoes such a kind of hydration, dehydration cycles, obviously the mechanical stability will come down. So membrane thinning will happen. So that creates a kind of micro cracks on the membrane, and that deteriorates the life of the membrane over a period of time. So the life which is less for the transport application is also one of the reason of membrane thinning that is happening, which is undergoing hydration and dehydration cycle so frequently. I think, can I take another question? I think it's coming from Dr. Rajua. So he is asking about, can you please comment on the performance comparison of fuel cell electric vehicles and battery during uh, cold weather conditions? Yeah, I mean, the fuel cell vehicle so far it has been demonstrated up to 5,000 hours. I think the battery is also depending because the vehicle wise is okay. Only if you replace the battery, then vehicle is also the battery cycles in terms of cycles undergo 2,000 cycles. The people are claiming. So the fuel cell electric vehicles, it's proven is up to 5,000 hours of operation cycle right now.
Sir, does the cold weather conditions affect these the performance?
Yeah, exactly. Actually, because the fuel cell at sub-zero conditions are very low temperature, the kinetics rates will be slow, and you need to because though the fuel cell will produce heat actually, uh, the 20 to 30% of performance will be less when you operate at a low temperature uh, compared with the high temperature operations actually. But there is a mechanism to heat up the system to and make the system which is on par with the ambient conditions. But if you operate as such, it won't be any issue.
Thank you, sir.
Dear participants, if there are any further questions, you can ask.
No, sir.
Okay, okay.
So if there are no further questions, then we would like to extend our sincere gratitude to Dr. Balaji Rangarajan Garu, despite his because he is the senior scientist in the CF Center for Fuel Technology. Besides his busy schedules, so he accepted our invitation at a short notice to deliver a couple of sessions on fuel cell technology. And these sessions are very wonderful, and our participants are uh, appreciating and they are thanking us for arranging these kind of very informative and useful sessions in our FTP. So we thank you very much, sir. So you are that is so you are flexible enough to accommodate any changes that we are bringing at the moment. So
No
today
issues.
itself it
Actually,
happened.
I was thinking that my session is 6 actually, so I was ready with that, so I could able to obviously meet out the whatever the requirement you say. No issues actually.
Yeah, so we are, so thank you, sir. So the couple of sessions taken by Dr. Balaji Rangarajan Garu has taken us through uh, how hydrogen is transformed from being a hazard to a sustainable energy vector, and the various types of fuel cell technologies and details about the working principles. And moreover, the session not only, even though it is a basic FDP, the sessions are not only providing us the basic principles, but they have given us the cutting edge research which is happening through their center. So we thank you very much, sir, for sharing with us whatever the research things that are happening in your lab. and encouraging us to just take up that as a research path. So thank you, sir.
Thank you.
Thank you very much.
Thank you.
Yeah.
Thank you for the opportunity also, and I am open to have any further questions through email also. Thank you.
Yeah. So dear participants, so we will be sharing the slides for the both the sessions, and we
Yeah,
will be sharing
I will send
the
you the slides. Yeah, no issues.
yes, sir. Thank you. So we will be sharing the contact details, that means the mail of our resource person also, so that if you have any further questions, you can you can draft a mail. Thank you very much, sir. Have a good day.
Thank you. Thank you. Thank you all.
Dear participants, the feedback link for the first session will be given now into the chat box. You please fill it for the attendance and you please provide the feedback also. So we will start our session 2 for day 5. So within a few minutes. So meanwhile, you please provide the feedback through the form. So we will be dropping the link for the feedback in the group, sorry, in the chat box. Welcome, sir. Dr. Sandeep Kumar garu. Am I audible, sir?
Thanks. Thanks for inviting me.
I request participants to mute their mic.
So, please let me know when I need to start.
Okay, sir.
Or maybe if you want, if we need to wait for a couple of minutes for people to join, we can start
No,
after.
sir. We are ready, sir. So just let us have the privilege of introducing you to our participants.
Okay.
Then we will start our session, sir.
Sure. Thank you.
Okay, sir. Dear participants, so we are here for the session 10 of day 5. So Dr. Sandeep Kumar garu is the resource person for this session. So he is presently working as an associate professor in the Department of Energy Science and Engineering at the Indian Institute of Technology, Bombay. He holds a PhD in renewable energy from the Indian Institute of Science, Bangalore, and a BTech in mechanical engineering from NIT Silchar. With academic and industry experience spanning Infosys Technologies, Tapar University, and IIT Bombay, Dr. Sandeep Kumar garu has built strong expertise in biomass gasification, hydrogen rich syngas production, waste to energy systems, and thermodynamic analysis of energy processes. Dr. Sandeep Kumar has authored numerous high impact journal publications in peer reviewed journals and presented his work at several international conferences. He has led multiple sponsored research projects funded by DST, MEDA, IRCC, IIT Bombay, and the Tata Center, and has also contributed to consultancy assignments in thermal systems and combustion technology. He is a recipient of the Young Faculty Award from IIT Bombay and holds patents related to gasification technologies and low emission burner design. He has many Indian and international patents also to his credit. His research interest combines experimental modeling and techno-economic analysis to advance sustainable and clean energy solutions. So I request all the participants to join me in welcoming our esteemed resource person for the session, Dr. Sandeep Kumar Garu. We thank you very much, sir. Now the session is yours. So I will, you please take over the session, sir.
Yeah, thanks a lot. Thanks for a nice introduction. And it's always privilege for any teacher to present or to take a sort of a lecture in front of new sort of a set of people. And I'm honored to have a sort of a lecture in front of teachers itself. So I hope means being a teacher, I would be able to sort of impart some sort of a new knowledge, that you may take it and take it forward to your students. So that way I would like to present and just one minute. So my PPT is visible.
Yes, sir, it is visible, sir.
Okay. So today I would like to take a sort of a topic of the biomass gasification and green hydrogen. So this is sort of a green technology and carbon neutral technology. So before that we get into the hydrogen, first we need to understand the biomass and gasification process. Then slowly we will move into the green hydrogen sector, and how do we produce green hydrogen from gasification and biomass. So first we need to understand that biomass is also an indirect form of solar energy. So basically biomass it stores the solar energy in chemical bonds with around 2 to 6% radiation to chemical energy efficiency, and that way it has been able to capture a lot of CO2 from the atmosphere, and combined with water and the solar energy, it is converting into the carbohydrates, hydrocarbon and oxygenated hydrocarbon organic molecules, which builds the whole sort of a life system. So typically that's why when we look into sort of a biomass energy, it is considered to be carbon neutral. So when we say carbon neutral, it is sort of because it is capturing CO2 when a plant grows and becomes a tree, and if we are burning it, then we can say that okay, part of that CO2 which is going directly into the atmosphere without any usage. Or if we say that okay, these plants or the is getting decayed, composted, and then it will be some bacteria, some insects and all, which will be eating it, and they will also release CO2 back into the atmosphere. So when we look into the sort of waste to energy technology or biomass energy systems, it is actually the biomass which has captured the CO2. It will again release back CO2, but within that, we are trying to capture some useful energy and product out of it. So that's why this is called what we call the biogenic CO2. It is nothing but carbon neutral system, where the same amount of CO2 which was captured by biomass, we are just releasing that, not more. So basically, when we look into the hydrogen, biomass typically contains around 55 to 65 grams of hydrogen in its organic molecule per kg of biomass on the dry basis. So it is not much, but it is one of the basically the molecular mass of the hydrogen is low. That's why the overall mass is low. But volume fraction wise, or if you say the amount of hydrogen that we have in our biomass, our body, it's significant. Now coming to the biomass potential, when we say renewable energy, sustainable and non-sustainable. So there are various ways we can actually get the biomass potential. So one is, say, agro industrial waste. So this is something waste coming from the paper mills, waste molasses from sugar industry or any food processing industry, textile and all. Then we have agriculture waste, which is earlier in the traditionally it used to be fuel or fodder, but slowly it has becoming a waste where farmers are burning it in the fields to get rid of. But if that particular agriculture waste, which is biomass, we can use for sort of energy generation, then that is also sustainable. Same thing about the municipal solid waste, which is typically coming from our kitchen. Biodegradable waste such as food and kitchen waste, green waste, paper, inert materials like fabrics, cloths, which has a sort of a origin from the biomass. Then another category which is sustainable is the forest waste, which is logs, chips, barks, leaves and all, which are actually forest waste, or even when we say the garden waste. So you can relate it to your college campus and all. So your college campus must be having many trees, park, gardens and all. And then there are a lot of dried leaves, dried tree branches and all, which is collected. Similarly, from the forest also, a lot of such biomass is collected, which are like dead biomass uh, parts, or the dry leaves, dead branches and all. So that is also a very sustainable source of energy. And typically, if we look into the history, this forest waste was actually fueling the kitchen of the whole world. And even now, more than 50% of the population is dependent on biomass or wooden based chulha, and all those woods are coming from this forest waste. Nobody cuts the trees to get the wood for the chulhas, but it is just the collected waste from the forest and those trees which is there. One sort of a thing which is the energy crops. Here there is a question of sustainability. So there we can say that, okay, energy crops like plant which is exclusively grown in their sort of a plain, it could be questionable. Say for example, Brazil, they are cutting on the Amazon forest, so they cut down the Amazon forest and grow sugarcane to get ethanol. So when we see that perspective, we don't see that the overall carbon balance is same, because you take any sort of a farm, whether it is a wheat, paddy, sugarcane, bamboo, any sort of a fruit farms or palm trees or sugarcane, the carbon dioxide capture capability that they have per unit area of land, it is very, very low compared to a thick forest, which is sort of matured for thousands or millions of years. So when we look into a same land footprint of Amazon rainforest, the CO2 sequestration capability is significantly higher compared to a simple sugarcane field. So we can't say that that is carbon neutral. It has to be sort of some sort of a extra carbon dioxide that we are not able to capture through the sugarcane fields. So this particular thing sometimes becomes questionable in terms of whether it is green technology or green energy. But yeah, rest of the this which comes from the actually waste or residues, they are definitely green energy and sustainable source of biomass energy. So now coming to the can I reduce that? Okay. Yeah, so when we look into the sort of a biomass, there are three major verticals through which we can get the energy. So one is the biological, which you can associate with the biogas plant or bioethanol plant. There the biological route or the microbes, they feed on the biomass in the absence of oxygen. So they give us some intermediate fuel like ethanol or methane. So if we give them enough oxygen, then they will also eat completely and release CO2 and H2O. But under the anaerobic digestion or anaerobic condition, they release methane or bioethanol. So that is what is one way of getting energy out of that. Another is the chemical way, which is chemical processing being done on certain organic molecules. For example, like biodiesel. So biodiesel is a very fine example of chemical where a very thick, long chain fatty acids are sort of a cut into short chain sort of a fatty acids, which actually give us a suitable fuel which is suitable for a diesel engine or the substitute for a diesel. So that chemical processing for fats or oil or fatty acids is something which comes under this chemical process. The other major process is this thermochemical. So thermochemical is again one of the oldest process that we have mastered, especially this combustion. So you can understand or appreciate the role of this combustion or the control over the fire which has on the growth of the human civilization. So we would say that this was one of the major sort of a milestone in the uh, human civilization, that was the control over the fire. And that is a thermochemical conversion where the heat and the chemistry associated with the heat plays role to give us energy. So combustion which directly give us energy, and two other process, gasification and pyrolysis. So they give us intermediate fuel, just like bioethanol, biogas, or biodiesel. These are intermediate fuel, which actually producer gas is hydrogen and carbon monoxide. This we will discuss. So our topic for discussion today will be this gasification pathway, and then pyrolysis, which gives us bio-oil. So we will discuss this part, thermochemical conversion, and then we will try to understand that this combustion, gasification, and pyrolysis, they are not very different process altogether, but very much interlinked. And to understand gasification, we have to understand combustion and pyrolysis as well. So now coming to different technology, every technology is not very suitable for every type of a feedstock. If we look into any biomass, most of the biomass is having cellulose, hemicellulose, and lignin as the major component. So typically when we associate with any food or this thing for human consumption, then whatever the simple sugars, carbohydrates, and protein and fat, they actually fall in this 5 to 13% of the categories, which is fruit. But when you look into a whole tree, then the fruits like say mango or apples, they make only few small fraction of the overall mass of the body of the tree. And within that tree body, majority of the component are the cellulose, which are the sort of a higher sort of a molecule or polymers which gives sugar, and then hemicellulose, which are the higher sort of a polymers of pentose sugar, and lignin, which are for the phenyl propyl based sort of polymer, which gives the strength to the trees and the plants. So they constitute the major part of the biomass. But when we look into the different pathway, biological biogas, they require only, or typically bacteria work on cellulose only. So they eat cellulose and convert it to biogas. When we look into bioethanol, they work on the simple sugar, like simple glucose sugar and pentose sugar, which they won't be able to digest this, but they want simple sugars that is part of this 5 to 13%. So you have to supply them the simple sugary juice like sugarcane juice or any fruit juices and all. Then only they will be converting it to ethanol. When it comes to the sort of a biodiesel, that also works only on the fat or oil or fatty acid. That is also part of this 5 to 13% component only. So some of the process like this chemical, which is biodiesel, and biological, which is biomethane and bioethanol, they are very much restrictive to the type of biomass that they can act on. So they are not very flexible in terms of feedstock. But then comes the thermochemical pathway. So thermochemical pathway, you can identify that combustion, gasification or pyrolysis. Say combustion, we can actually use any biomass with low moisture content. You can identify that anything that is dry, you can burn it, whether it is a simple wood or dry leaves. Dry leaves are rich in cellulose, hemicellulose. They will also burn. The woody biomass like tree trunk and branches, they are rich in lignin. They will also burn. And even the simple oil that we use in our home during Diwalis or pujas, that is actually fat or fatty acids, or the oil that also burns. So it doesn't matter. You can even take the sort of a rice or dry sort of a wheat and put it in the fire, it will also burn. So basically any sort of a biomass which is having carbon, hydrogen, and that is making the fuel. It can undergo thermochemical conversion. So combustion or thermochemical conversion is the most flexible pathway in the bioenergy systems where the limitation is only on the moisture content. So now coming to the thermochemical conversion thing, combustion where we say that involves complete oxidation of biomass fuel to CO2 and H2O, which with the remaining as ash, which are the inorganic solids. So we know that in any biomass in our body, we have sort of a blood, so we have iron in it. We have sort of a bones, so we have lot of calcium in it. All our body part, we have lot of salt running in our body. So we have sodium, we have chlorine, we have sulfur in our DNA. So all these things which are actually not fuel, like say sodium, nitrogen, in protein we have nitrogen, so iron and all those things, they make actually the ash, which doesn't burn or oxidize to give energy, but they remain as powdery ash or solid residue at the end of combustion. So it is one of the oldest process used by human civilization, especially for the energy purpose, light and heat, as well as safety and security from the forest animals. So predominant fuel, you can use any type of a biomass, whether it is oil seeds, agro residue, tree branches, trunk, dry animal cakes. All these things can be burned reasonably if it is reasonably dry. So now coming to the trying to understand the gasification. So basically, first if we understand how this combustion is happening, so try to understand how this flame in the matchstick that is glowing. So the first thing comes that, okay, this biomass is actually a solid fuel. But is this flame having a fuel which is solid? If you just blow air, it will flicker. That means something gaseous is here, right? Where is the solid fuel burning, or what is the characteristic? This is the solid fuel burning. That is the red hot charcoal. So this charcoal which is burning, if you blow air, this will not move anywhere because carbon is here, which is fuel, and oxygen will react here. But when you blow here, some of the fuel particles, which is gas, will move here or there. So this is actually gas. But now the question comes from where this gas is coming. Now this gas is coming from the process called pyrolysis. So as the name suggests, pyrolysis means heat which breaks down the organic molecules. So whenever we ignite this matchstick with this tip which is having a sort of a phosphorus based flammable material, we ignite using this. So main sort of function of this ignition process is to supply heat to this biomass. So say this particular flame, so once this tip burns like this flame, this will supply heat to this biomass which is near to it. So once this biomass gets heat, then those organic molecules, which are mostly the composition of most of the biomass, is having carbon, hydrogen and oxygen, and the bond starts breaking down. So when the bond starts breaking down, those solid molecules break down into smaller molecule, and because the temperature is also high, they will get into the gaseous phase. And still those smaller molecules are also hydrocarbons or oxygenated hydrocarbon, or it could be even carbon monoxide or hydrogen or methane, which will enter into this zone where already temperature is there and oxygen is also coming here. So this flame actually makes the fire or oxidation of the fuel, which is product of this pyrolysis. So we call that volatiles or the tarry gas. So this volatiles or the tarry gas which is coming out of this pyrolysis will burn here and will then supply heat to further to this wood, and this flame will continue till we consume all the wood. But this pyrolysis also gives another residue which is this charcoal. So that we can identify whenever we burn a wood, we will have some charcoal coming out, and that charcoal will burn at the end like this simmering hot charcoal that you can see here. So this particular thing is now oxidizing with oxygen in the atmosphere or undergoing combustion. This carbon is releasing heat. Now, so we know that pyrolysis, that is first that is happening, and then the combustion of the products of this pyrolysis happens. One of the product of the pyrolysis is this volatiles or the tarry gas which burns in this flame, and another byproduct of the pyrolysis is this solid char or the carbon which burns like a solid flame. But then what is the gasification process? So now the gasification process is basically, technically, by definition, it is a substoichiometric combustion of fuel with an oxidant, and the major sort of objective of this is converting the solid biomass fuel to the gaseous fuel. So very simple definition, conversion of solid fuel to a gaseous fuel is biomass gasification. So in this process, what happens is, we don't let this carbon gets oxidized. What we do, we use this carbon as a reducing agent to give us this fuel, which is hydrogen and carbon monoxide. So typically what happens is, when we heat biomass, it undergoes pyrolysis, gives us volatiles, which is mixture of many higher hydrocarbon, carbon monoxide, H2, CO and all. And then it also gives 20 to 30% by weight charcoal, which is mostly the carbon, and also ash will be entrapped into that. So in gasification, what we do is we only let these volatiles get oxidized to H2O and CO2. We supply oxygen or air only for that. And then what is the role of charcoal is, charcoal then reduces this H2O and CO2. So reduction process happens, charcoal, which is carbon, reacts with H2O to reduce to carbon monoxide and hydrogen, and charcoal reduces carbon dioxide to 2 moles of carbon monoxide. So here the charcoal acts like a reducing agent, which gives us this fuel gas, which is carbon monoxide and hydrogen. And here comes the process of gasification, which we say that whatever the solid fuel, that is biomass, getting converted into gaseous fuel, which is rich in carbon monoxide and hydrogen. So I hope everybody understood this process. If anyone has any doubt or something, please stop me in between. We can take up the question or doubts, and we can discuss that in between also. So now again, coming to the differentiation of pyrolysis, gasification, combustion with respect to the how much air we are supplying. So here again, if we go back to this matchstick, so what we understand is we will supply only air or oxygen for this combustion of these volatiles to get this flame, but we will not let this charcoal sort of react with oxygen, but it will react with the product of this flame, which is CO2 and H2O, and then we will get carbon monoxide and hydrogen. So that is the role of char in the gasification process. So here, when we look into the pyrolysis, it happens in the absence of air. So equivalence ratio is 0. So equivalence ratio basically means how much air we are supplying in proportion to the actual air required for the complete combustion. So when we say equivalence ratio is 1, we are supplying enough oxygen for the complete combustion, and there comes the combustion process, which is near to the equivalence ratio of 1. When we just heat it, in the absence, when we don't need air, that is pyrolysis, where just heat is required. Okay, so gasification falls in between, where we supply around 20 to 40% of the required oxygen, where only the volatiles they actually burn, and the charcoal reduces it to give us hydrogen and carbon monoxide. So that is the major difference of gasification with respect to combustion and pyrolysis. Now again, if you want to discuss or understand how this process is happening together, it is very difficult to visualize how it happens, but with this simple figure we can understand. So when we supply heat, when the heat goes, when the temperature is roughly more than 100 degrees or so, then the drying process starts. So drying process, all our moisture from the biomass will start coming out. And when the temperature goes beyond 200 degrees, so at more than 200 degrees, those hemicellulose starts degrading. Around 220 to 250 degrees, cellulose also starts degrading, or it's a sort of organic molecule start breaking down. and the lignin, it starts at around 400 degrees. So at more than 200 degrees, our pyrolysis or the breaking down of organic molecules starts, and it gives us charcoal and the tar or tarry gas or the volatiles. And then when we supply air or oxygen, this charcoal and tar are exposed to the oxygen, and temperature is also high, where the temperature is more than ignition temperature. So the both the fuel charcoal or the tarry gas can undergo combustion because both are fuel. But what favors the combustion or the type of fuel is the tarry gas. The simple reason, the charcoal, if we look into this charcoal oxidation process, it is very, very slow. You can imagine that when you burn any sort of a wood, in maybe in 15-20 minutes, all the flame will go off, but this charcoal will still be simmering for another half an hour or so, where this charcoal is only 20 to 30% of the weight. So basically, it's solid to gas reaction, where carbon, which is solid, reacts with the gaseous oxygen. The process of this reaction process is very, very slow. So that means if a limited amount of oxygen is available, most of the gaseous fuel, which is the tarry gas, it will consume oxygen. There won't be any oxygen available for this charcoal to get oxidized, even though they are present in the same place. So the sort of a you can say the chemistry favors the oxidation of the tarry gas, and charcoal remains unreacted. And we get here the products of combustion of tarry gas, that is H2O and CO2. And then the next process of reduction happens, where the CO2 and H2O reacts with the residual charcoal, which is hot because it requires energy. The temperature is high because of the combustion of these volatiles or the tarry gas. The temperature is high, and then we react carbon with the CO2 and H2O to get hydrogen and CO2. So all this process happens in tandem together. Only how much air and oxygen we are able to control, that gives us this gasification in a single reactor. So these are some of the sort of a major reactions. So combustion, carbon can oxidize, volatiles or the tarry gas can oxidize, but we know that volatiles or the tarry gas will have a more preference to get oxidized. Both this will release heat. Then in the reduction zone, the carbon reacts with H2O and carbon reacts with CO2, and both are endothermic reactions. So you can see that both the reactions are endothermic, and that's why this heat, which is supplied by this hot charcoal, is very much necessary. But this charcoal becomes hot because it was present in this combustion zone, so the temperature is high, which favors these two reactions. And also there are some other reactions which involves hydrogen, where carbon monoxide also reacts with H2O to give us hydrogen. This is mildly exothermic, so small energy is released in the process. And also carbon reacts with H2, that is hydrogen, to give us methane. That also releases small amount of heat. But we can see that this is solid and gas reaction, so this is relatively slow, and this is also relatively slow. So we have to design the system such that these reactions get enough time for the reactions to happen. So now if we look into, I will just give a sort of a brief history. Maybe 2 minutes I would spend on this. So where this gasification process or system came into picture. Actually, the story starts from the Second World War, when the Allied forces, they made a sort of a strategic sort of a decision that they will cut down the supply of petroleum fuel to the Europe. So by that time, German forces or the Nazis, they have captured almost whole of the Europe, and Europe is a place which doesn't have much of a liquid petroleum availability. So there is a lot of coal in the Europe. Germany itself has a lot of coal mines, but the petroleum, liquid petroleum availability is very poor in Europe. So they were majorly dependent on the import, especially from the Gulf countries. So, but now they were allies of the UK and US, so they made a strategic decision that no fuel will be supplied to the Europe so that military vehicles won't get any fuel to run. So that was a strategic policy or decision by the Allied forces. But there were two scientists called Fisher and Tropsch. So they came up with a very nice catalytic conversion process, or you can say a polymerization process, where carbon monoxide and hydrogen, they polymerize to give you long chain hydrocarbons. So carbon get rid of oxygen and react with hydrogen and makes a long chain. So controlling the temperature and the type of catalyst, actually you can get anything from C2 molecules to C20, from simple ethane and butane up to the wax. You can get it from the carbon monoxide and hydrogen. So, but from where they were getting carbon monoxide and hydrogen was through the coal gasification. So coal was very abundant in Germany and whole Europe. So, and coal gasification was already a known technology. So it was actually a major source of hydrogen that time when natural gas was not a major sort of exploited much. So coal gasification is more than a century or maybe more than a 1.5 century old process that we know, and it produces carbon monoxide and hydrogen. So that coal is converted to syngas, and that syngas was put into this Fischer-Tropsch, that is popularly known as FT synthesis or Fischer-Tropsch synthesis, to give liquid fuel. And that liquid fuel, which was similar to petrol or diesel, they were supplied to the military vehicles. But because the process was costly and the production was limited, because they have to go for a mass scale production and all, and it was a wartime. So Fisher and Tropsch actually within few months they came up with this technology and they started putting up a big plants. But still the petroleum was very limited, and Nazis made a decision then in whole Europe petrol and diesel will not be available to the civilian population. So no civilian petrol pumps used to have petrol or diesel. So that particular time, another set of scientists, they came up with the idea that if you can gasify coal, why can't you gasify wood or the biomass? Because engines can run on this gaseous fuel, which is carbon monoxide and hydrogen. And in fact, for the matter of fact, the first IC engine, which was based on the Otto cycle, it was tested in hydrogen way back in, I think, 1805 or 1810. It was the early 19th century. The first IC engine was actually tested in the hydrogen fuel. So a gaseous fuel was very easy to be used in the IC engine with some small modification. So that time researchers came up with the biomass gasification technology, or what that time they called wood gasifier, because they were just using the solid wood, which has a very low ash and operates well. So this small gasifier behind this car that you can see is the gasifier which generates carbon monoxide and hydrogen, which goes into the engine and runs the engine. This tractor has a gasifier in front of it, and then this small two-wheeler also has a gasifier mounted behind. So you won't believe that there was a company in Poland which just during the Second World War, 7-8 years or so, they actually retrofitted these gasifiers in more than 1 million sort of what you say vehicles. So more than 1 million vehicles were retrofitted with this uh, gasifiers. But they were quite popular at that time. But when the Second World War got over, cheap supply of petrol and diesel were there, then suddenly this technology just died out. And then again got revived in 80s, 90s as a sort of a renewable source of energy. Okay, so coming back to the process, now this is a very simplistic diagram of a one downdraft gasifier, which will help you to understand how the sort of a process happens in a single reactor. So in a single reactor, if you see, first we have this reduction zone where we put the sort of a charcoal to start with, and just assume that it is under the steady state condition. So volatiles are here. This is a combustion zone because we are passing air here. So when air is passed, this zone gets the availability of the oxygen. So pyrolysis is happening in this zone, and then when the pyrolysis happens, volatiles comes down because we are drawing the gas from the bottom. So because we are drawing the gas from the bottom, so all the gas, volatiles, all these gases flow from top to bottom. So when this pyrolysis, after this volatile gases enters into this combustion zone where air is available and temperature is above ignition temperature, they start undergoing combustion or they start burning. So that we identify as combustion zone. And then at the bottom where you see that the red line or red dots are ending is the place where oxygen is now zero. So all the volatiles will consume oxygen, and that will become the start of the reduction zone. So below that you have charcoal, and over it the CO2 and H2O is coming out, which is the product of this combustion zone. And then charcoal or the carbon start reducing this CO2 and H2O, and at the end you get carbon monoxide and hydrogen that is taken out of this system. Now this pyrolysis gets the heat from this combustion zone. How this combustion zone is now hot, it is around 1000 degrees or so. So through radiation, because we use biomass particle which has a bed porosity, or means there are some gaps in between. So that way the radiative heat passes from this combustion zone to the upper zone, and as we move up the temperature comes down. So this yellowish part is where we have a temperature up to 200. So from it will vary from 200 to around 600, 700 degrees as we come down. And above that in the green zone, it is temperature will be less than 200 degrees, where only drying process will happen. So this zone keeps supplying fuel or volatiles to this combustion zone, and combustion zone continues to supply heat to this pyrolysis zone and also to the reduction zone. And charcoal, which is produced from this pyrolysis zone, converts the gas or the CO2 and H2O to the producer gas, which is CO and H2. So that way all this process, drying, pyrolysis, combustion, reduction happens in a very single reactor in a self-sustained way. We don't have to supply any external heat or control the sort of a temperature artificially or something. It automatically happens in a single reactor. So that is the beauty of this process of gasification. So now we will come to the green hydrogen. That is sort of a theme of this topic. So when we look into the gasification process, it is also one of the way we can generate hydrogen from this. But whatever we discussed till now, it was air gasification. So air gasification, it has a limitation that typically any biomass which has 50 to 70 grams, 55 to 65 grams typically, if we take average 60, we can't get more hydrogen out of it because it doesn't have hydrogen into it. And also because getting all the hydrogen is not possible, some of the hydrogen comes out from the system in form of methane or H2O. Maximum 35 to 40 grams of elemental hydrogen we get in the product gas. And that too, when we have the gas diluted by nitrogen, because we are using air which has almost 79% nitrogen, which doesn't participate in any of these reactions, come out as a gas, inert gas, which occupies a lot of volume. So it occupies around 45 to 50% of the volume, which leaves that hydrogen as a desired product has only small volume of around 20%, and also the product yield of around 35 to 40 grams. So there comes the limitation which can be overcome when we look into oxy-steam gasification. So where oxygen, we can use it to increase hydrogen volume fraction by eliminating nitrogen. So it will eliminate nitrogen, and then we can use steam, which acts as a gasifying agent. We can enhance hydrogen yield by using carbon and carbon monoxide through the water gas reaction in water shift reaction. So what here happens here is basically it eliminates the limit of 60 grams of hydrogen that is present in the biomass. We can we can induce hydrogen through the steam, and both the thing together we can club it together to get the oxy steam gasification process. So the role of steam basically here in the hydrogen production is, even in the pyrolysis zone, the steam reacts with the volatiles to give hydrogen through steam reforming. to water gas reaction where carbon reacts with H2O to give us hydrogen, and also carbon monoxide reacts with H2O to give us hydrogen. So basically it is the carbon source which reduces H2O to give us hydrogen, and so technically part of the hydrogen that we get is actually coming from this water or the steam. So as we saw that typically biomass which contains 50 to 70 gram gives only around 35 to 40 grams. But typically we get 100 and more than 100 grams of hydrogen through oxy-steam gasification, which is more than 200% extra steam, that hydrogen that we can get from the process. Sorry. Yeah. So here we can see that as we increase the steam to biomass ratio, so x-axis is steam to biomass ratio. So means we are injecting more and more steam as we move in the positive x-axis, and y-axis is our hydrogen yield. As we can see these black dots, as we increase steam, the hydrogen is increasing from around 65 grams, it goes more than 100 grams. And that at the expense of carbon monoxide. So you can see that H2 to CO ratio is also increasing, means hydrogen is increasing, carbon monoxide is reducing, and there this reaction, water gas shift reaction, is mainly the responsible for that. So as you can see, when we increase the oxy-steam gasification process 0.4 to 2, the hydrogen to biomass ratio, then we actually get around more than 66, we go to 104 grams of hydrogen. So there comes also the role of waste heat or the solar thermal systems, where we can see that typically the input energy in the oxy-steam gasification, biomass input energy is 75%. We require oxygen, so we need to use an air separator, which consumes energy, that is typically 5% of the input energy. And then the residue around to 20% of the input energy is actually from the for the steam, and that we need at the temperature of around 400 degrees centigrade or so. So there come the beauty that with just around this 25% of extra energy input in terms of steam and oxygen separation from air, we are actually able to more than double the amount of hydrogen that we are getting. And also another fact is that if we are able to generate saturated steam at 100 degrees, 80% of the enthalpy requirement is met. Means if we have any small waste heat source, or if we can use the solar thermal systems which can give us a low temperature steam, we can still fulfill the requirement of the sort of a major requirement of the energy for steam generation. So clubbing this two technologies, waste heat or solar thermal with biomass, we can actually get a complete more hydrogen efficient system, and which has the potential to convert around 40% waste heat or the solar heat energy to the chemical energy in hydrogen. So that is a sort of a beauty of the system, oxy-steam gasification. So we are also working on this particular sort of a project where we are feeding the biomass waste into the system and use the gas for the running the IC engine, and the IC engine generates the waste heat. That waste heat is used to generate steam, which goes into the reactor, and also part of the gas we are using for the upgradation and then separating to get more hydrogen into the system. So when we look into the feedstock, what type of feedstock that can go into the gasification system, as we said earlier, thermochemical system can take any dry biomass, only moisture content should be low, typically less than 20%. We can use it any type of biomass. And if we look into different biomass here listed, the carbon, hydrogen and oxygen content, you can see the variation is very small. So variation is very small. That's why the gasification process, which is a thermochemical process, the major thing is how much is the carbon, hydrogen, oxygen composition, and the variation is very, very small across all the different biomass species. So it doesn't make much of a difference what type of biomass you're using. whether it is like coconut shell or tree branches or the agro residue made pellets, and or this is actually a chicken litter, which is also organic, dry in nature, then dry flowers or any wheat or paddy straw. Anything can be used as a fuel for the same sort of a design of a gasifier. We don't need to do much of a modification. Only based on some parameters, we just need to change the process parameters, but the reactor remains the same. It is very agnostic in nature. So one of the requirement is that we need to make the pellets, because we need to give some porosity for the flow of gases and air through it, and also to supply radiative heat to the biomass particle. So that way our biomass, whatever the powdery biomass, can be made pellets using a pelletizing system. And this is also one of the another sort of a waste which we can use in gasification is the refuse derived fuel. It may not be actually coming from the biomass source, but it could be even plastic and such things like paper, cardboard and all, which can be used as a sort of a fuel, which we typically call the refuse derived fuel, which is coming from municipal waste. When we look into the role of plastics, actually, the plastics gives more sort of a hydrogen. Plastic contains 15% hydrogen compared to 5 to 7% in biomass. So we have done our lab experiments on that, and we got more hydrogen from when we increase the sort of a plastic content. We have gone up to 25%, and the cold gas efficiency also increased, as well as the calorific value of the gas also increased, because it was getting enriched with hydrogen more and more. So even adding this another type of a waste, which is waste plastic, it enhances the performance of the gasifier and the quality and calorific value of the gas. So another sort of a work that we have been doing is this on the entry and flow gasifier, which can take sort of a powdery biomass. The process and all remains same, but the capacity throughput is quite high. And here we can use plastic up to 75%. So that is the sort of a benefit of that we have been doing with the Monash University in Australia. So with experiments here, and I will not go into the details. Another sort of application of the biomass gasification process that we have developed in our IIT Bombay campus is the decentralized waste management. So here we are doing the campus waste management project that we have taken. It is funded by the Alumni Association. So we have got a good funding for that. And we are actually targeting the garden waste, which is we are collecting around 500 tons of garden waste per year. So they are nothing but the dry leaves, branches, dry flowers and all that typically all of you will have in your sort of a college campuses also. And it has roughly 70% of the organic material. The rest 30% is the dust, soil and all, because when we collect, the soil is also collected together. But out of that, we also get plastic and cardboard and packaging waste, which is nowadays quite huge. After the COVID era, the online sort of purchase has increased, and this so has the plastic and cardboard packaging waste. And also another type of a waste that we have been handling is the sanitary napkin waste, which is actually technically a medical waste, but is disposed as a civic waste, and it has a very high moisture content, 80 to 90%, but still in a small fraction, we are able to gasify it with the rest of the biomass waste. So this is how what we have been doing. So this is a typical garden waste that after collection from all our roads, buildings, gardens and all, we collect it. And then this is the plastic waste which we collect from the packaging waste and from the messes like bread pieces, the packet of the food material and all. And then we shred it, and then we make the shredded biomass and plastic, we mix it, and then we pelletize it. After that, we get the mixed pellet, which is biomass. So this is 20% plastic and 80% biomass. And then we have used it in our canteen. So this is one of the setup that we have installed in our one of the canteen that is catering in to the staff. So it is staff canteen. Every day lunch for around 400 people is cooked on the system. So we collect this biomass, make the pellets here. This is the garden waste, and then we make the pellets, and that is fed into this gasifier. And the steam cooking. So at the back you will see that is a steam boiler which is fed with this burner. So this burner, you can see this thing. So gasifier generates the gas, and that is burned in this specialized designed burner, very low emission and high efficiency, high temperature sort of a burner, which generates steam, and that steam then goes into the sort of a cooking system inside the kitchen. So this is the steam cooking system where rice and dal is boiled, the milk is boiled, and this chana, rajma, and all those things whichever require boiling, it is cooked. And also we are shortly putting up a sort of a idli maker where idli will also be cooked using the steam here. So here we are sort of converting around 1.5 to 2 tons of the garden waste generally, and because of the fire hazard, we actually generally send it to outside, where we have to pay to the BMC municipality around 50 lakh rupees, because it is organic waste and we have to pay fine to give it to them. But after incorporating this system, we have an opportunity to save around 90 tons of LPG and 300 tons of CO2 emissions annually. So right now in this particular system, we are saving around 10 kgs of LPG daily. Now we are putting a bigger system in a student hostel, which is of 500 students capacity, where we will be starting that in the end of December. And after that, another 2 more hostels we will target, where together we will have a 90 tons of LPG savings annually. So this sort of a model can be implemented in any big education institutes and all, which has a usage in terms of student messes, canteens and all, and also we generate a lot of waste. So another type of a sort of a waste, that is sanitary napkin waste, also we have done the gasification in it with around 4%. So 4.8% we have loaded it. This is the sort of pictures with the actually water loaded napkins, but once after the installation and testing, we have actually used the actual sort of a sanitary pad, which is the blooded sanitary pad, which we collected from the women's hostel. So this is typically collected around 6 tons per annum, which also we have to give it to the sort of municipal corporation for medical incineration process. But there also we spend lakhs of rupees to give it to them. And this thing we can easily manage, because this will continue make around just 2% of the total garden waste that we collect. So we can easily manage within this sort of gasifier. So currently we are saving around 10 kgs of LPG per day, and we will be implementing it around for 500 students hostel next month. Another sort of a application that gasifiers has in the thermal application. So you can see that typically when we look into the biomass, it has a cost of around less than 1 rupee. So typically less than 1 rupee will be the cost. When we look and compare it with LPG, the cost is around 2 rupees per megajoule. For CNG, it's around 1.5 rupees per megajoule. For diesel, it is more than 2 rupees. For furnace oil, also more than 1.6 rupees. And for electricity, it is the highest, the 3 rupees around. So only the cheaper one is the coal, which is cheaper typically than biomass. But wherever these applications are used, like LPG, CNG, diesel, furnace oil, or electricity, we can actually convert it into a biomass-based system. And there, sort of these burners, specialized burners we have designed, so which are very low in emission. So temperature is also quite high. You can see the temperature, we get more than 1100 degrees temperature. Hello, anyone has any query? Okay. So 1100 degrees compared to a conventional burner. Yeah, somebody was saying something.
Yes, sir. Can we know about the design, sir? Designing of that gasifier, sir? The details of that gasifier. What is shown in the previous slide?
Yeah, this one.
Yes, sir. Yes, sir. That one. That one.
Yeah, so this particular one is actually a 10 kg per hour.
Not this one, sir. Not that one. The next one, sir. Next one, I think. Next slide, sir. No. This one, sir.
This burner.
Yes, sir. This burner, yes, sir.
Yeah, so this is actually just a burner, which is actually a premix. So this is our patented technology. So one of the PhD student had worked on this. So we have created sort of a very low emission and uh, high efficiency sort of a burner. Its efficiency is as good as LPG burner, even though this is a low calorific value fuel, but we have achieved the efficiency as good as LPG burners. And also it takes care of all the particulate matters and ash which comes from the gasifier. The design is that. So means actually, if anyone is interested in this gasification technology or something, we can sort of work together. But this sort of a thing is with very much sort of, you can say, a patented design that we can't disclose right now, the design and all, but definitely we can work together to, if you want this installation in your campus for any research purpose or any application purpose, we will be happy to sort of collaborate and work together on this particular aspect.
Okay. Thank you, sir. Thank you. Thank you.
So the emissions are quite low. So this is the conventional burner temperature, which is less than 900. We have gone to around 1150 degrees or so. The so emissions of the conventional burners is high, where our emission in the new burners are quite low, both NOx and CO. And also we have worked on this is actually a flameless combustion burner. In the flameless combustion burner, the flame we don't even see outside, it gets inside the burner. So that is very much useful in many of the industrial application where uniform heating is required. And the emission is like very, very low. Even compared to normal LPG or natural gas burners, it is even lower than that. So you can see that this is a typical normal burner application, but in a flameless, it completely, all the flame, all the combustion zone goes within the burner only. So here the temperature is very, very uniform. So that you can see that across the axial distance and a different height across the height, the temperature is 1050 to 1150, a very uniform temperature. That is what is the requirement by the many of the industries for thermal application. And the emissions are very, very low than the CPCB norms. So very well accepted in the market. And this is one of the things that we are working on, the aluminum sort of a melting. So this is comparison with the conventional burner, the NOx and the CO emission. And this is another application where it is for the cooking, but in the direct cooking. So the gasifier is installed outside the kitchen and the gas is supplied to the burners. So one of the pipe supplies to the burner where this cooking is happening, another is going to this big sort of a tawa where chapati or dosa can be made. So this sort of systems also we have designed, and this is one from one of the sort of ashram school in Amravati. So similar three sort of installations that we have done for such schools, and in some of the applications we are installing the steam-based cooking system, where only steam enters into the kitchen or cooking system. The gasifier remains and the burner also remains outside. So this is one of the application in the industry where the sand drying. So this is one of the implementation we have done in the Kolhapur sand industry, where for the sand drying, they were using the diesel that we have replaced with this gasifier system, and they are using it for past 2 years. And also we are now designing a bigger system for them for the sand reclamation, which requires a temperature of more than 650 or 700 degrees. So these are some of the things which are where a lot of thermal applications are used in the sort of industries which can be fulfilled by this green fuel biomass using the gasification technology. So here I would end my presentation. So I think, yeah, we are 8:30 only, so we have still a lot of time. If anyone wants to have any discussion or any query, we can take that. We have a lot of time for the discussion now. So anyone has any query or something, we can take up the questions now.
Yeah, participants, the session is open for QA now. So I request the participants to ask if they have any questions.
Sir, good evening, sir.
Good evening.
Uh, I want to get clarified whether long chain carbon or short chain carbon particles are required for complete combustion. Which kind of biomass is having long chain? What will be the range? Can you explain brief on this?
So actually for the gasification process, there is no as such restriction which type of thing you will require. Say for example, lignin. Lignin is having the most complex and long chain molecules and all heavy molecules, like you find mostly in the woody biomass or coconut shell waste and all. And if you look into the sort of a rice straw or wheat straw, that sort of a thing which has mostly cellulose, hemicellulose, they are relatively shorter chain, but all of them are equally good fuel. So it doesn't matter in terms of gasification, because when we do the pyrolysis takes care of all the variation and converts that to sort of a shorter chain molecule in the gaseous phase, and then we oxidize that or burn that. So it doesn't matter which type of molecules you have, organic molecules you have in the biomass. The pyrolysis process will take care, and uniformity is there in the combustion and the reduction zone.
Thank you, sir. Thank you.
Okay, I've got a question in the chat box. So what is
Sir,
the
good
I think,
hello.
yeah, please. Yep,
Yes,
please.
sir. Good evening, sir. Thanks a lot for the explanation with a simple matchstick that entire pyrolysis process and the biomass burning. My doubt is, sir, uh, what are the risks involved in pyrolysis process and the gasification process? That means, what are the challenges I want to know?
Yeah, so actually, I would say that when we have the system, which is this particular technology, we have worked a lot. So I would say that in India, we have been working from almost 80s onward. So it started in IIT Bangalore, where I did my PhD. So it started then, and now we have got very good control over the process. So different type of designs are there for different application, for thermal, even for power systems, or even for oxy-steam gasification for hydrogen production. So the technology is quite mature now. We don't see much of a challenge. Only thing is with the two things, when the moisture content is high. So for that we have to do pre-processing like drying process. So we have to get the moisture content below 20%. That is one thing. And another is the high ash, where some of the ash components, especially the alkali metals, they actually create issues in the process, which forms clinkers, or ash fusion happens, and they actually damage the reactor walls and all from the inside. So for that, we have also, so the gasifier system that I have shown, so this we have designed for high ash, where we can go with the ash content of more than 20% also. So typically the paddy straw, which is having very high ash and all, so that also we can manage and gasify here. So typically these are the two main challenges, the ash content and the moisture content. So moisture has to be removed outside the reactor through drying process. And then ash, we have made the design in such a way that it takes care within the system also. So in pyrolysis and all, not much of a problem happens. Only the correct sizing as per the design or the size of the reactor, we have to give it the right size of the particles so that the bed porosity is there. And then the system works without any issues or challenges. I hope I answered your question.
Yes, sir. Thank you, sir. Thank you so much.
Welcome. So there is one question in the chat by Mr. Ramachandra. So what is the ratio of plastic waste and garden waste in pelletization? So typically, one of our PhD students who just finished his PhD, so we started with 5% plastic. We went up to around 40% plastic, but we found that up to 25% plastic is what we can manage for the continuous operation. Because one of the issue is with the high amount of plastic is plastic doesn't give much of a char. The fixed carbon is very low in plastic. It will give just 2 to 5% of char residue. And as we discussed here in the chemistry, the char is required to reduce CO2 and H2O to give us hydrogen and carbon monoxide. So if we go for more than 25% of the char, the process becomes unstable. We get very poor efficiency and gas quality and all. So, but up to 25%, the system runs without any issue. The hydrogen content is high. The things works well. So 20 to 25% is good that we have gone, and we are making that pellet. And not only with plastic, we have done experiments with paper, cardboard, even leather and all. So, and everything, the things are working fine. So, not issue as such. So, any questions from anyone, please? You can discuss.
Sir, there is one more question in the chat, sir. It says, how, that is, what is the binder that is used during the pelletization? Just to
Okay.
make, yeah.
Yeah, so binder actually depends what is the feedstock, because typically if the biomass has good amount of lignin in it, the lignin acts like a very good binder when we do the pelletization process. So typically, if you go for sawdust pellet making, or even our garden waste, because our garden waste has branches, small twigs and all that has lignin content. So that helps in binding. So when we do the garden waste pelletization, we don't use any binder. But yeah, in some of the waste, like if you say that bagasse, that or groundnut shell and all, so we have to add some binders, which are either we can add some sawdust waste which is having high lignin content, or even we mix like this, what we call the when we wheat chaff, if I'm not wrong, what technically it is called. So when we grind the wheat, we get this atta or the refined flour, and then the residue of that actually is high in lignin, so that is also used as a binder. So what we call in Hindi as choker. So it is not actually husk. Husk is for rice, so that is very high silica content. So that is not good for binding and all. But the wheat chaff, so that is good. And then some of the other which are also used for different application, like even the sort of a cellulose syrup is there, that is used. And in some cases, if lignin is enough, a little bit of 5% or 2-3% of water spraying, that also helps in good pellet making or stabilization of the pellets. But typically, depending on the lignin content, the binder is decided. And in most of the sort of a waste, binder is not needed. Or for some sort of a type of waste like groundnut shell or bagasse and all, so it is very much needed. So when we have cotton stock, we don't need binder. When we have coconut shells and all, we don't need anything. So for some, it is required, and we use the lignin component to substitute that. So now the one question is how the sun is converted into hydrogen syngas. How the syngas is converted into hydrogen. Yeah, so actually we have to separate the hydrogen from that. So there are some standard technique like PSA and all. So where PSA, we pass the mixture of gases and it removes hydrogen from, or separate hydrogen from other gases. So, or there are membrane separation process, and also in our lab we have developed an in-house zeolite based separation process. So zeolite is used and it removes CO and CO2 and methane, and only hydrogen is delivered after the separation. So there are many ways we can actually separate hydrogen from the mixture of gases in the syngas. Any questions from anyone?
So there is one more question from the participant in the private chat. So how well that means how better it is when compared to stubble burning?
Stubble. Okay. So when we look into the stubble burning, we are not getting actually any, you can say the value out of it, no energy. And also when we burn it open or open burning, it pollutes a lot. So pollution there is not CO2, but the pollution is those soot particles that uh, creates the sort of a health issues of PM 2.5, PM10. But when we do the gasification, we actually convert it to very clean gas, which is carbon monoxide and hydrogen. And when you burn it in a burner for air, we can get any heat or electricity or hydrogen through it. So we can generate money from the waste. That is one thing. And second thing is the process is very, emissions are as good as any sort of a, you can say a natural gas or LPG sort of a engines or burners and all. So emissions are very low, so pollution is also quite limited. And because it is biogenic, so CO2 is here not considered to be a sort of a pollutant here because it is biogenic or the renewable CO2. I hope I answered your question. So is the gas storable or any condition we have to maintain? So actually gas is storable. It's not an major technical issue, but only thing is that it's the regulation issue. So because it has carbon monoxide, so which is poisonous, so it is not recommended to store it. So you generate the syngas and use it without storage because still there are no guidelines or this is suitable like what should be storage pressure, the container material or other safety regulations and all are not there. So it is not recommended to go for storage, but it can be stored. So that is not a problem. So typically for our lab experiments for characterization and calibration of the gas analyzer and all, we actually get the mixture of gas from the gas supplier who gives us the compressed sort of a this gas composition, same that we have, and we store it in a cylinder and keep it in gas. But in the uh, in the market there is no regulation, so it is sort of not recommended to do that. So is there any method to separate the CO from gas? Actually the same process. So CO we have to separate it from the this thing, the syngas, using the PSA or any other membrane separation as you read separately. So basically if what we say, uh, use it and then store it, that's fine. So then again you have to carbon monoxide, you can flare it, burn it, or use it in any heat thermal application, and hydrogen you can store it using the standard hydrogen storage technology process or technique. Another question, can you please tell once again how fluidized bed gasifiers provide more gas quality compared to the fixed bed? So actually, it is not about the quality of the gas that it gives better. The fluidized bed gasifiers are used when you have a high capacity requirement. So fixed bed gasifier, because the biomass particle size is bigger, so the heat transfer takes time for the pyrolysis to happen. So heat has to penetrate say a 1 centimeter particle, and then the pyrolysis will start once it goes beyond 200 degrees or so. So that way the process becomes slow. So the same size of a reactor, I would be able to gasify less biomass in a fixed bed or a drowned off reactor. But if I reduce the particle size to millimeter or 2 millimeter and use it in a fluidized bed or an entrained flow gasifier, then the pyrolysis will happen very quickly. So in the same time, in the same size of a reactor, I can actually gasify 10 times the biomass compared to a fixed bed. So that is the one sort of a benefit. When it comes to the quality of the gas, quality is of the gas is not an issue, because actually entrained flow gasifier has much more challenges compared to fixed bed because it operates at very high temperature. But what I discussed was the entrained flow and fluidized bed gasifier can take more sort of a plastic compared to the fixed bed because the temperatures are high, so they can in the pyrolysis process only lot of volatiles get converted directly to carbon monoxide and hydrogen. So that way we have gone up to 75% of plastic content in the entrained flow gasifier. That is not possible in a fixed bed gasifier. So that is a sort of some benefit actually. Okay. Any other questions from anyone?
Yeah, participants, if there are any further questions, please ask. There are no further questions. Then we have come to the end of day 5, session number 10. So, thank you very much, sir. So, Dr. Sandeep Kumar Garu, for accepting our invitation and delivering this session. When we made a very nice narrative of a very important and very interesting topic, and it is like a story that anyone couldn't miss. So, thank you very much, sir, for making this session very good narrative of
Yeah,
very
thank you.
interesting topic.
Yeah, thank you. Thank you very much for giving this opportunity. Always love to come to the new audience. So it was means online, so could not see the faces and meet the people, but I always love to meet new people, interact with new people and all. It always, as a teacher, it always a sort of a privilege to discuss the things with a teacher so that they can also take some knowledge to their students. And I hope some of the things they can share with their students and when they go back to their college and all. So I will be happy with that. So I'm really thankful to giving me opportunity into this faculty development program. Thank you.
Thank you very much.
Okay, so I will take a leave now. Thank you.
Thank you. So, dear participants, that is it for today. So, we will meet again for tomorrow's session. So, I would like to just keep a reminder that tomorrow our session starts at 2 o'clock. So, from 2 o'clock to 6:30. So, we have 3 sessions followed with the test and feedback session and then validation. So, I request all the participants to join the session on day 6 at 2 o'clock. Thank you very much and good night.